All right. So it's huh? It's so weird that I can't hear it. Is that good? All right. I don't know why. It must be some other acoustics. It doesn't travel up past this thing maybe, but oh. Let's see if I get this to open. All right. So I think originally I had that individual assignment set to be that Wednesday after we get back. I meant to have it set for the end of the week, so I've changed that now. So that'll be due kind of at the end of the week, that week we get back from Thanksgiving. The first part of it's a NOVA, so maybe I would kind of suggest if you've got time to kind of work on this before break and everything, try to work on that part because it'll be pretty far removed by the time we get to the due date up for it, and we're just going to keep talking about regression stuff from here on out. So maybe try to work on that first question. Other than that, we left off thinking about linear regression, kind of looking at the relationship between an X and Y variable. So I'll show you how we do this in Excel today. Before I do that, I want to bring up kind of one point, and then we'll take some examples. I've got a couple files up under the in-class data folder. I also updated the slides, so I've thrown a few more slides in here than what I had earlier in the week. Kind of looked at these coefficients. So let's think about, if this doesn't screw things up. So let's think about, I can estimate the relationship between any two variables, right? But there's probably a lot of other things that matter, right? So let's think about a example where, let's say at first I was just running a regression on crime and the amount of money spent on the police force, okay? So here, what I was doing before was looking at crime rates and said, okay, what's the correlation between those and police expenditures? So you would think if a county or a state, however level we're looking at this at, if they were to spend more money on their police force, what do you think would probably happen to the predicted crime rate? Intuitively, you would think that this is probably negative, right? You spend more money on your police force, crime rates go down. Problem is, if you run this simple linear regression, I don't care what aggregate level you're looking at, county, city, you will always find, if you run this simple linear regression, probably a positive value. So the reason why is because what areas do you think are probably spending more on their police force? Areas that have conditions that are apt to leading to high crime. So low income rates, right? High unemployment, right? Being, just kind of impoverished areas. So if we don't control for that, then yeah, it's going to look like police force expenditures are positively correlated with crime. However, if we can start to add in things, I think that's what I have on the slide, so we'll just go back there. If I start to control for these economic conditions, so I throw in this additional variable, which is unemployment rate, well, now the interpretation of our coefficient, and I'll start writing, we're including several regressions on that, or several regressions, several X variables on that right-hand side. But usually we'll stop writing these like A and B and kind of use these betas, right? That's typically what you see if you go look at an academic paper or anything like that. Once you have more than one variable, you start to kind of call those coefficients beta, right? Here's beta 1, that's the coefficient on my first variable. Beta 2 is the coefficient estimate for my second variable, so on and so forth. Okay? And I can include as many variables that are on the right-hand side as I want. Now the interpretation of my coefficient on police force expenditures becomes the effect of a 1 unit increase. Well, here that'd be like spending $1 more on my police force would increase predicted crime rates by beta 1, right? Holding constant any other variable I've included on that right-hand side. So now it's like, almost like the thought experiment is holding constant unemployment. So two counties with the same unemployment rate, but one of them spends an additional $1, and we probably wouldn't change that to like thousands of dollars, but an additional $1 on their police force, what would the change in their crime rate be? And now we probably start seeing what we would expect. This is very small, which is that this is negative. It's like loud enough here. Be in that room, right? So then we would probably get more of like the expected sign of that coefficient because we're controlling for these other factors we know that matter, right? We'll control for these other factors that we know are also related and also allow us to make predictions about crime rates. Okay. Does that idea make sense there? So, you know, if we've got the data, we want to throw as many things on that right-hand side as we can. Right? Well, that's not, there's some other issues, but for the sake of this class, as far as we're going to go, if we do have the variables, we want to include them on the right-hand side, right? If you want to take like the advanced stats, you start to deal with some issues of over-identification and things like that. But for the sake of what we're doing, we want to throw as many variables on the right-hand side there. So, you know, how would I figure out what these coefficient estimates are? It's the same as what I talked about last class. You would take a derivative, right? I'm trying to minimize the sum of the squared error terms. It's just now to come up with my predictions for y. I'm using a lot more variables to predict y, so I'm probably going to be making smaller errors in my predictions, right? But I want to choose these coefficients such that I've minimized the sum of those squared errors still. Now we can't visualize this now. I could show you like when we had one variable on the right-hand side, right? It was a two-dimensional, I could think about what the errors were. When I start adding more variables, it's like first I'd have like a 3D kind of like not just a line, but something that's like curving, and I'm choosing the coefficients so that it's minimizing all my errors. And if I start including more, I've got something that's not even three-dimensional. I can't even visualize it. It's like the bunch of matrices, and it's hard to even think about. Right? But the general idea is still the same. I am trying to minimize how far off my predictions are from the actual y values by choosing these optimal coefficients. Okay? So I can take that equation, I just now have to take a derivative of it in respect to however many variables I've added, right? Each one of these coefficients plus the intercept. I then have n equations, n unknowns. I can solve for each one of those things. Now, we don't want to do that like by hand. It's especially if I had like 10 variables, this is really nasty. You can actually, I think here, I put a link up for the actual, like you can walk through the proof. It's math. It's not overly exciting, but Excel will do this all behind the scenes for us. And then we just want to be able to interpret what those coefficient estimates mean, right? So I think, oh, one more thing before we go to Excel. We'll also have this measure, and we're going to not calculate this by hand either, but Excel is going to do it for us. It's going to be called R squared. So the R squared picks up what percent of the variation in our y variable or our left-hand side variable that we can explain with all of our x variables that we've included on that right-hand side. Right? So we're taking all these x variables on the right-hand side to make predictions about the y variable. How much of the variation in that y variable are those x variables explaining? And I say how much, more specifically, what percent, okay? So the way that we're doing this is we're looking at the difference between the predicted y's and the average y, and then the difference between the actual y and the average y's, and then taking a ratio of the two. So it's basically like how much of the variation using our predictions can we explain of the total variation that exists in that actual y variable. Okay. So we'll start interpreting R squared. When we look at this regression output, we'll start interpreting these coefficients, and I'll show you how we do this in Excel. So the first one, I have this COVID regression file. So ANOVA testing is great, but it's very limited, right? We say we can only control for a couple factors. So here I've got what the number of June cases, October cases. This was the percent vaccinated. Probably should have relabeled this. Whether or not it was in a metro area, the year and the month, or actually the month here is wrong because I only pull October here. And then kind of all these different counties, right? So here's your county ID numbers. So maybe I'm interested in something like, okay, how did the cases in this past month in October, right? How were they related to the percent of people who were vaccinated? So I go data analysis, regression, hit OK. My y variable I'm thinking about is the number of cases they had in October. I then kind of took a look at, okay, my x variable, sorry, and I didn't explain that well. So I went to my data analysis tab. I then clicked on regression. All right? I forgot we haven't done this yet. So hopefully I have that data analysis tab in there. I go down and find regression, hit OK. My Y variable is the number of cases that these counties had in October. So Control Shift or Command Shift on a Mac, I just selected that entire row. I'm then going to click on my X variable. So the variable I want on the right-hand side is this % vaccinated. Okay, so I'll select that entire column of data. I selected the labels, right? So I don't, I want to make sure that Excel treats those labels not as a data point, but just the labels of my two variables. So I make sure that's selected. I'm going to put this on a new worksheet. You will never choose this constant is 0, right? Anything that we do, we're never going to select that constant is 0. We don't want to add new confidence intervals. It always defaults and gives us the 95% anyway, so that's fine. And then we don't need to click any of this other stuff either, right? Just keep it simple. We've selected our X variable, our Y variable. We hit OK, and it spits it out, all this regression output over here. Okay. So let me zoom in on this, and I'm also going to write out exactly what we did here so we can match up what we're doing in Excel. It's like if we had to write this out. So what I just did was thinking out there was, I want to try to predict the number of cases. I know that there's going to be some intercept value, and then I want to know what's the relationship between the number of cases and the % vaccinated in those counties. Okay, I'll go back here in just a second. All right, so this is what I'm trying to get estimates for: the intercept and that slope coefficient. Okay, so all I did there, right, to get this output was go to my data tab, data analysis, go down to regression, and then I'm just selecting that left-hand side or that Y variable that I wanted. And then I'm just selecting the column of data that has that X variable that I want. Okay. Yeah, so here, let me see if I can get this up at the same time. Oh, there I am. So where's the little talking thing? So notice, I want my Y variable or my left-hand side variable to be the number of cases in October. I want the X variable, how I'm trying to explain the number of cases, is based off of the % vaccinated in that county. Right? That's something I think is probably correlated with the number of cases they had. So my Y variable, I'm just selecting the Y variable, my X variable, which is October cases. For my X variable, I'm selecting that % vaccinated variable column. Okay. Any questions on that? Okay with this so far? So I hit OK. I'm going to hit cancel because I already did it, but we hit OK. We go to that output, right? And we can start to analyze this. Okay. So notice it throws like these confidence intervals over here. We generally won't do anything with these. We're really just going to focus on the coefficient, its corresponding p-value, and then like interpreting what that coefficient actually means. So here, for every additional person that's vaccinated, it looks like the number of cases actually goes up by 540 people. And it's very significant, right? That p-value is essentially 0. And remember, our null hypothesis is always that this coefficient is 0. So here we can reject that, and that we found really strong evidence that there is actually a really high positive correlation between the % of people vaccinated and the number of cases. So it kind of doesn't make sense, but why? Well, if you think about it, the % of a population that's getting vaccinated, it's probably that areas like in inner cities that are more likely to see COVID spreads were probably the ones that started to get vaccinated at higher percentages first, right? So there's probably something that we're not picking up here that's correlated with the % of people getting vaccinated. Maybe in lower income areas, we see, different vaccination percentages. And so, just to help the lower income, they have less availability of healthcare. There's tons of stories we can tell. We only have a simple linear regression. We're not capturing a lot of the story, right? In fact, what % of the number of cases is explained by the % of people vaccinated? Or R squared is 0.03, so only 3%. So it looks like there's a lot of other factors that would tell us or allow us to be able to predict the number of cases in a county more than just the % of people that are vaccinated. Right? I'm guessing these are things like income, even the population. So we'll go back. And now I'm just going to start including some of my other variables here. So I thought I had population. I know I did when I, maybe I have the old one. Let me see. You got the one that you guys have. Do you see population as a variable on there? Don't. Well, why didn't I save that? Well, it won't be as interesting, but we can still get a good idea on it. So one thing that'll kind of control for population is I also kept in here the number of cases those counties had in June. So it's almost like I'm kind of saying, okay, I know that there's different baselines for these different counties. I want to control for kind of where they started, right? I'll also kind of include whether or not it was a metro state. So we'll add in a couple of additional variables here. So I'm going to go to regression, my Y variable. I'm still going to be looking at the number of cases they had this last October. Then my X variable, and kind of notice that that's nice instead of scrolling up and down. When I click on these arrows, here, I'll show you this again. So select my Y variable all the way at the bottom. Once I click these arrows, it'll send me back out to the top. So I don't have to scroll up all the time. So I'm now going to, I still am interested in that relationship between the percent vaccinated and the cases, but I'm now going to control for like, is it in a metro area? And also what was its kind of baseline, right? What was the number of cases this area had in June? Okay. So all I'm going to do is select these three variables, hold Control and Shift or Command Shift on a Mac, hit the down arrow. So I'm going to select them all at the same time. Okay. Questions on that? Okay with that? All right. So I selected my labels, so I make sure that's clicked, and then I'm going to hit OK. All right. So it spits this output out on another sheet. We'll blow this up a little bit so we can actually read it. Well, notice I got a really high R squared here, but that kind of makes sense. Once I'm starting to control for the number of cases they had in June, I'm probably picking up a lot of those other factors that I thought mattered, right? Because a lot of those other factors would have influenced what the cases were like in June. So anytime I have like a previous measure of the variable, a lot of times it's a really useful control, right? Because it kind of tells me where I'm starting out. So now if I'm looking at this, right, looks like kind of if I had, how can we interpret these variables? So if I had a higher number of cases in June, it predicted that I had a higher number of cases in October. Well, that makes sense, right? The cases that probably were seeing higher COVID rates in June probably saw them higher rates in October as well, right? Relative to other counties. Okay? But we'll kind of focus on interpreting this percent vaccinated in this metro. Okay? So if we think about this percent vaccinated, it was measured as percentages, so 0 to 100, right? So the way we interpret these coefficients is a 1 unit increase in the X variable causes the predicted Y value or Y variable to change by whatever that coefficient estimate is. So here, getting 1 more percent of your county vaccinated would decrease the number of cases by 14 people. Right? Now, like I said, ideally, I would have had this population there. We could look at population per 1,000 people or something like that. But at least this is telling us that, we're picking it up very highly significant, right? 0.007. So with 99% confidence, right? This p-value is less than 0.01. So with 99% confidence, I can reject that there's no relationship between the percent vaccinated and COVID cases. Or said differently, I found pretty strong evidence that there is a correlation. Right? Now, is that magnitude large? It seems pretty small, but it's significant, right? So at least there is, you could say with 99% certainty, there is some change. Right? And not only can I interpret it that way, I forgot to add on the last thing, which is once I start adding in additional variables, it's still that interpretation, but holding constant the number of cases that county had in June and their metro status. So the thought experiment using this data that we can say is 2 counties with the same number of cases in June, they were both either in a metro area or non-metro area. If one of them got 1% more of their population vaccinated, they would see their COVID rates fall or COVID cases fall, right, by 14. So I can say holding these other things constant, it becomes a really powerful thought experiment. This regression output is like very useful for decision making, right? Especially when I can start including a lot of important control variables there on the right-hand side. Okay. Any questions on that before we keep going here? And you know, this is kind of a nice example that kind of highlights, if I just run this simple linear regression, I'm going to get some really what we call bias coefficients because I was omitting other variables that were really important. Okay. So we'll have a little discussion about that, and then we'll kind of look at some GPA data. So we kind of already talked about this, but right, if I don't have important control variables, I'm going to get some bias in my estimates. More specifically, I can think about another example. Let's say I looked at that birth weight and mother smoking one. So I end up seeing that it's negative, but is that really telling me that smoking is causing lower birth weights? So what do you think, maybe be a little stereotypical here, what do you think is probably true about mothers who smoke while pregnant? Probably on average, if we look at the data, they have lower education levels. They usually come from lower socioeconomic status backgrounds, right? It's not that they're like malicious people. A lot of it's just like there's a lack of education, right? So what do you think is probably true about lower income areas when it comes to like birth weight here being higher is usually better? So what do you think about if you think lower income areas? What's probably true about the health status of their children? Probably not as great as people who have access to better health care, can purchase better foods, right? Can, you know, all these other things. If I'm not making a lot of money, right? Like I'm not probably buying and taking prenatal vitamins. Right? They're actually relatively expensive. So, you know, we're probably picking up a lot of these other negative effects that come from low education and low income in our smoking variable if we don't control for those. Okay? So you will see a really high, I think in last class, it was like negative 253 grams. Smoking while pregnant doesn't decrease the birth weights by that much. It does decrease them, but not by that much because we're really picking up the effects of all these other things, lack of proper healthcare, lack of good nutrition. And once we start controlling for those, yeah, it's still negative. I've looked at it, it's definitely still negative, but it's not near as high, okay? So we want to think about and be very careful because a lot of the times we probably are omitting variables that are important. Our data sets aren't always complete. We're probably missing something, right? Remember, we're trying to make predictions about our Y variable. We're probably not getting all of the predicting factors that we need. So we will kind of think about these like this is affecting this. But we need to make sure that it's not causal, right? It's just that there's a correlation between these things. Now, as I add in more variables, that's a stronger correlation. Now, I can say that there's a correlation between percent vaccinated COVID cases, even after I'm controlling like for their baseline cases this summer, after I'm controlling for the metro area, if I threw in other things like population, income level, well, that correlation holds a lot more value, right? When I can control and hold constant all these other things, but it's still just evidence of a correlation, right? I can't completely say it's causal. We have a couple more tools that we would need to use in order to say that, which we won't explore in this class, but if you're interested, I think 321 is the next stats course within the building. The guy who's teaching it is really, we just had these second or third year here. And it would probably be a very enjoyable class, also very useful. He goes into a little bit of like R, which I don't know if anyone has heard of that, but a lot of companies are expecting that you have some ability, and not necessarily expecting, but it's a huge plus if you have any ability to do some familiarity with R or Python, right? Those are kind of coding languages. It's not like ones and zeros, right? It's coding, but it's somewhat user friendly. In fact, this is a plug. I would suggest, I mean, you guys are already probably on good trajectories because, you're you. But one thing to set yourself apart that's really valuable, and I know a couple other honor students that did it like their last year. I would maybe wait to do it until your last year so it's like relevant. But you can go on a website called DataCamp, and they have free R and Python classes you can take there. I think there's a way you can get some money from the university to pay for it. Don't hold me to that, but I think that there's a way that like you can apply for like some grant, some funds that are available for students to do that. But this is really useful. Even if you just go through the free ones and have some familiarity with it, it's definitely worth it. But anyways, that's my spiel. Okay. So back to this. So, right, about correlation and causation, right? Some things that can go wrong. Maybe it's X that's causing, or sorry, maybe it's Y that's causing X, not X that's causing Y. Like maybe I have this relationship kind of flip-flopped. Maybe it's something that's missing from the regression that's causing both of them. So this is the idea. I think the very first week of day of class, I said, murder rates and ice cream sales are positively correlated. We're in a regression. We'll see a huge positive correlation, very significant. Well, it's because we're missing this outside factor, which is weather. Murders tend to be higher when it's hotter outside, and ice cream sales tend to be higher when it's hot outside. So we're missing maybe this other thing, Z, right? We're omitting an important variable. Okay. I always like this little thing. Like I used to think correlation implied causation, right? Then I took a statistics class, so now I don't. Sounds like the class helped. Well, maybe, right? Because maybe it wasn't the class that actually helped me understand it. It's just that it was correlated with other things that helped me understand it. It's terrible. So the other one that's really good in case of this, that shows like if you're missing this outside factor Z that's causing both of them. Here's like a plot of autism rates and organic food sales. If I run a regression on monthly or annual data, it will look like these are highly positively correlated. I don't think anyone is suggesting organic food sales are causing autism rates to go up, right? It's probably that there's some things that are linked to both of these, like we've had an increased focus on health, right? And so more people are buying organic food. Maybe autism rates are probably being diagnosed at higher rates because we're getting more people into the doctor. We're getting more people focused on health. Could be that, some other factors that we're not even thinking about that are correlated with both of these things, right? So here is a proof, and I'm not going to make you go through this. I think we'll focus a little bit more on this on Monday, but basically if I leave out an important variable, so let's say X2 is this other important variable that I've left out of my regression. When I go to get my estimate for the slope coefficient between X1 and Y, right, the variable that I use in the regression, the coefficient estimate that I get will include the real effect, but also this additional component, right? And this additional component has something to do with the relationship between the variable I included and the variable I left out, okay? So this is what we're going to call, this would be like the bias that exists, this second term, because our slope coefficient should be giving us basically what the true coefficient is, or the true population coefficient between these two variables. However, if we leave out an important variable, we'll have this additional kind of bias in there. And we'll talk more about that bias and then can we put a sign to it on Monday. But just for now, let's just know it exists. Okay? So I think here, the other example I wanted to work through today is another example where we see some evidence that if we omit an important variable, we can come up with very different conclusions. Okay, so maybe I have this data set. I think I called it GPA omitted, maybe up there on Canvas. And I've got all these different college students. I have what their GPA is, whether or not they're an athlete, what their SAT score was, all this other information. So if I just run the regression of GPA on athlete, I'm going to take a look at that coefficient. If I then do the same thing, but I now control for the SAT score of the student, now what happens to the estimate that I have, okay? And you kind of can imagine, if I use this naive approach with only one variable on that right-hand side, I actually end up looking, it looks like athletes have a negative effect. Being a student athlete has a negative effect on your GPA in college. And, that's what I wanted to say. So, you think about, a lot of people, they have a stereotype maybe of the intellectual capability of athletes. At D1 universities, it's not a stereotype. Like if you look at the football team kind of GPA, much lower than the average student body, much lower than a lot of the other sports even, right? In fact, football and basketball programs are like the only sports that come into, what's it called? Some type of like academic ineligibility. The NCAA will sometimes actually put bans on teams and things if they don't meet certain academic criteria. It's only those two sports, right, that are hitting it. So maybe that there's if we're not controlling for the kind of base intellectual ability or ability to do well at school, right, then we're going to end up with a pretty biased coefficient. So maybe we want to include SAT scores, and then we can include some other variables as well, right? And this is an interesting question, because being a student athlete, it takes a lot of your time. Even if we control for the person's SAT score, right? And maybe that it has a negative effect, right? Because you've got a lot less time, you've got a lot more responsibilities, but also maybe it's teaching you time management skills, and maybe it's teaching you kind of leadership skills or all these other things. And so does it have a positive or negative effect? We'll find out, okay? So here I have the GPA omitted variable file. You guys seeing that on Canvas there? So let's run the naive regression first, which is just going to my regression tool. I'm going to select my college GPA for what, about 4,000 individuals. And then my X variable, I'm just going to do whether or not they're an athlete, okay? Hit the arrow, I selected my labels, hit OK. So I get this output. With just that athlete variable, I'm explaining how much of the variation that exists in GPA is only about what, 0.8% here. So I'm missing a lot of important stuff. So I should take these results with a grain of salt. So I come down here though, if I wanted to interpret it, well, now we have one of these variables that's just a 1 or a 0. So the 1 unit increase would be if I see someone who's not an athlete compared to an athlete, right? Or going from being a non-athlete to an athlete, we would predict that that student's GPA would fall by 0.28. Okay? So that's pretty large in terms of GPAs on like a 0 to 4 scale, right? Also, the p-value is basically 0. E to the -9, remember that means move the decimal point 9 places to the left. So this is basically 0. So it's very significant, right? I can reject at all the significant levels, 10, 5, and 1%, or reject with 90, 95, 99% confidence. Right? But I'm probably missing a lot of important factors, right? So, someone runs this regression and says, yeah, being an athlete's terrible. We should get rid of all the athletics programs. Well, let's hold the phone, right? So, man, that was like the most 70-year-old thing to say. So let's go select my GPA as my Y variable. We'll then go to X variable. And now I'm going to just start just controlling for SAT scores as well. Right? So I'm going to select the athlete and the SAT variable, hold Control and Shift, hit the down arrow. So now I'm going to have this additional control on the right-hand side. And now when I look at the output, well, first of all, I'm explaining now about 16 to 17% of the variation that exists in GPAs. And the size of my coefficient on athlete has went down by quite a bit. So now I'm thinking about the effect of being a student athlete, right? Only predicts that GPAs would be about 0.05 lower. And here with a p-value of 0.26, in fact, I can't actually say that there's even any relationship. Because at a p-value of 0.26, I would fail to reject the null. The null is that the slope is 0, or that there's no relationship between being a student athlete and college GPA. Okay? And that's just from including one additional control variable. Okay? Now, how would I interpret SAT here? How would I interpret that coefficient on the SAT? Yeah, we would predict that that person who scored 1 point higher on the SAT would have a GPA that was 0.00192 higher. Right? Now, 1 point increases in the SAT isn't very much, so we wouldn't expect a very large change in the GPA, right? But then we can start to use these to make more interesting statements. So instead of just 1 point, let's say I wanted to know the effect of an 100-point increase. What do you think I would do? This is the effect of 1 point. Just multiply it by 100, and that would give you the effect of a 100-point increase. And now this is a little bit more useful, right? And it's a little more realistic. Right? If someone scores 100 points higher in the SAT, we would predict that their college GPA would be about 0.2 higher, holding constant whether or not they were a student athlete in college. Any questions on this? Okay. I'll show you something here. So let's say I want to come up with a prediction for a student, for someone's GPA, for a student athlete who scored a 1200 on the SAT. Okay. Well, if I think about what I've got here, come back to this in just a second. So I've got GPA, I've got being an athlete, and then I had SAT score. Once I have values for each of these things, right? I don't remember exactly what they are, so I'm going to make them up here. Well, might as well just look at them instead of making them up. So we had what? 0.68, 0.00192, and the athlete one was negative 0.0506. Okay. So if I wanted the predicted GPA for student athlete with a 1200 SAT, I can use these values to come up with my predicted GPA, right? If it's a student athlete, this just becomes a 1. SAT, I said they had a 1200. So 0.68 plus negative 0.05 times 1 plus 0.0019 times 1200. Right? So once I have these coefficient estimates, I can come up with predictions pretty quickly, right? So here, I would take the intercept, don't want to forget that, right? I would then add to that the coefficient on SAT times that person's SAT score, plus whether or not they're student athlete. I said there that they were, so that's a 1. And there I would get my prediction for the GPA for someone who's a student athlete. Okay. Any questions on any of that so far? Okay. So I can start to make predictions, right? I can start to look at the effect of different changes in these variables. You know, probably what's a little bit more realistic or more useful in this example. I move this. And I'm going to leave out this SAT squared. That's for something we'll probably do down the road. But let's just say we go to data analysis and I say, okay, look, I saw how much just including the SAT score influenced my coefficient on being a student athlete. So now I'm going to change my X variables so that I include everything over here. Okay. So I had some demographic information, total number of credit hours they had taken up to that point, their high school size, some other test score measure. So I'm going to hold Control and Shift, hit the down arrow, and select all of those variables. I left out the SAT squared because we're in a punt on that and hold that for another class. So I'll hit OK, change the view. I now see when I've included all these variables. I've now got up to about, I can explain about 30% of the variation in GPA here. I'm guessing a lot of this is like, you know, we don't have major choice. We don't have what university they were at. There's probably a lot of other things that would be useful in predicting GPA that we don't have. Okay? So we can explain about 30% of the variation that exists in GPA. And now notice when we include all these other control variables, now it looks like being a student athlete actually has a positive impact on GPAs. And the p-value is pretty much 0. So we can say that we can reject that there's no relationship at like any level, right? Very high levels, or with a high level of certainty, we could say that there is a relationship between being a student athlete and GPA. And in fact, the relationship is positive. Okay. Questions? Holding constant everything else. So the thought experiment is like 2 people with the same exact SAT score, same score on this verbal math test. Both ranked the same in high school, both either male or female, both either white or black, both have the total number of credit hours, both went to the high school the same size, but one of them's a student athlete and one of them's not. What's the change in their predicted GPA? All right, so that thought experiment, when we have all these controls, becomes really powerful. Right? 2 otherwise identical individuals based off of these characteristics, but one of them is a student athlete. What's the predicted change in GPA? Okay. Questions on any of this? Yeah.
Okay, so when we have all these variables that are like in different measurements,
Yeah.
how does it like just do that if they like mean different things?
So whatever your units are in, it's a good way to explain this. It's always looking at the relationship. It's almost like for every single one of these variables, the coefficients, like you could have holding everything else constant, let's say you had, oh, I don't know. So this was the SAT and here was GPA, right? Holding everything else constant, you could actually think about the effect of getting a higher SAT score on that predicted GPA, right? So here, the units of your SAT score is 1 point. And however you're measuring GPA, right? This is just like a scale, basically. This is kind of almost like unitless. The slope always tells you a 1 unit increase in X would cause whatever the slope is change in your Y variable. So your slope is always in the units of that X and Y variable. Now, so this was like your first coefficient. Now, if you think about your second variable, so let's say, oh, what was another one they had there? High school size, right? Honestly, I don't even know the units of that. It's like, if you look at it, I think it's like, they scaled it somehow, so I'd have to go back and look at it. I think high school size here, I forget. So it looks like it's kind of between 0 and 10. So they did something about like relative, I don't remember, but basically higher numbers is a higher high school size. I think maybe it gets up to 9. Maybe this is like in hundreds. So 900. No, it's gotta be higher than that. I have to go look back and look. Well, let's just assume that the unit was in hundreds of students. So like a 9 here represents 900 students. So there, if I'm picking up the slope for high school size, it's still a 1 unit increase, right? If I'm thinking about rise over run, so it's like change in Y over the change in X. Well, that change in X, that coefficient always represents just a 1 unit in kind of change in X. Doesn't matter what the units are, it's always just 1 unit. So if I go up by 1 unit in X, the slope tells me the unit change. Oh, thank you. I was drawing this out. I never switched it over. Sorry. So it's like almost like you have this, you can have a different graph for each coefficient. And all the slope is picking up is the change in X and then telling you what the change in Y would be. So whatever X units X is in, you're always picking up that unit change. And then it's the slope is always going to tell you the unit change in Y. So how does it pick up like the different units across different variables? It's almost like you're really analyzing each variable one at a time. So like I'm just looking at the units of Y to the units of X1. I'm just looking at the units of Y to the units of X2. Now I'm just looking at, right? That was that holding constant phrase. So I was only ever looking at the relationship between the units of each, one X variable and the units of the Y variable. It's another way to think about that. Yeah, like I guess I think anything you would graph out, right? To get the actual slope by doing the change in Y over the change in X, you're really kind of always keeping the units of the two goods, right, intact. And then the slope just tells you the change in Y from 1 unit increase in X, right? So if Y changes by 100, X changes by 10, what that slope is telling you is if you changed X by 1, that's how much Y would change by. Does that kind of get at your question?
Yeah, I was just curious how it happened when we had like 8 variables on the other side. But you explained
Yeah,
it.
it's basically like it's not a great way of explaining it, but it's almost like it like does each relationship one at a time. That is actually kind of what it does, but it's not like it drops the other variables. It's just that it's only looking at the relationship between Y and that one X variable, holding everything else constant, right? So it's almost like it's like out of the picture. All right. Okay. Any other questions? I think we'll probably end here a little bit early. So one thing I want to mention, so we'll kind of revisit this idea of correlation and causation. We'll talk a little bit more about the bias that could exist here. I've got some of those athlete regressions kind of in the slides. We'll probably start talking about, I don't know, I haven't made my mind up yet, either some log models, or we'll do some kind of squared, adding in some squared terms. So let's keep doing regression. So on Monday, I will not kind of meet in person in this class. I am going to set up Zoom on Canvas and then post an announcement with Zoom link. And I'll probably, so if you want to watch it synchronously, you can use Zoom and kind of watch as I kind of probably just do like a 20 to 30 minute little video. And then if you want to watch live and want to ask questions, that's fine. Or if once I post that video Monday, you can just watch it anytime next week. That also works for me as well. All right. So it won't be as long as the entire class period. It'll probably just be like I said, 20, 30 minutes. I doubt it'll be 30 minutes, probably like a 20-minute video going over kind of the next thing that we want to talk about with regression. And I'll just have expected that you watched it before we kind of come back in class the following Monday. All right? So I'm not going to see you guys for a while. I know, don't be too sad about it, but look for that. If you do want to sign synchronously, like I said, the Zoom link will be there on Canvas on Monday. Otherwise, I'll be pretty available, except for like probably Thursday to answer emails. So if you have any questions over break, feel free to shoot me an email. And because I won't have to be here, we won't be meeting next week. If you do have any questions, instead of office hours, send me an email. We could kind of do office hours over Zoom. So I'll be out of the area for a while. But yeah, enjoy your break, and I will see you guys. Not next Monday, but the following Monday. Okay.